right, today we're diving into a side of cybersecurity that's, well, a little different. We're not talking about viruses or malware. We're talking about hacking the fundamental laws of physics. Let's get into it. Yeah, I know what you're thinking. Hackers hack electricity? Sounds like a line from a movie, right? But believe it or not, this is the reality of a super fascinating and kind of scary field of hardware attacks. We always think of hacking as this battle of code against code, but what if the real fight is happening at the atomic level, right inside the silicon? I mean, just think about that for a second. What if you could break through the world's most secure software, not by finding some clever flaw in the logic, but by literally forcing the chip it's running on to mess up? That's exactly what we're going to unpack.
Okay, so how on earth is this even a thing? Well, it all comes down to a concept called fault injection. And the name says it all. It's about injecting a fault, targeting the electricity, not the code.
So, the core idea here is that computer chips, no matter how ridiculously advanced they get, are still just physical devices. And you know what? Physical devices can be messed with. If you can carefully manipulate things like voltage or timing, you can actually make a processor screw up a calculation at the worst possible moment. And this is where it gets really interesting. On the left, you have your standard software bug, right? A mistake in the code. You find it, you write a patch, you fix it. But on the right, that's a whole different beast. A physics-induced error isn't a logic problem. It's a physical event that forces the chip to get something wrong. And here's the kicker. You can't just release a patch for physics. To really get our heads around this, we need to go a little deeper. Why does this even work? Why can physics break a computer chip? Let's get back to basics on how these little electronic brains actually tick. So at the very core of every single processor, and we're talking billions of them, are these things, transistors. These aren't just abstract lines of code, they are actual physical switches that control the flow of electrons. And it's that physical reality that attackers have learned to exploit. You have to understand, for a CPU to do its job right, everything has to be perfect. The power supply needs to be rock solid, the internal clock that sets the pace has to be precise down to the nanosecond, and there can't be any weird temperature swings or interference. If you disrupt any one of these things, even for a split second, you get chaos. Okay, so we know these weaknesses exist. The big question is, how do attackers actually use them? Let's open up the attacker's toolkit, and you'll see it ranges from surprisingly simple to mind-bogglingly precise. First up, we have voltage glitching. This is kind of the brute force method. The best analogy is this. Imagine you're trying to read a sentence, and someone keeps flicking the lights on and off. You'd probably miss a word, right? That's basically what this does to a CPU. A perfectly timed dip in power can make the chip skip a critical instruction, like, say, the one that checks your password. Then there's clock glitching. This one is all about timing. See, every CPU has this internal metronome, this clock, that keeps everything in sync. If an attacker can just briefly speed up or slow down that beat, they throw the whole chip's rhythm off. An instruction might not get enough time to finish, making the CPU think a security check passed when it really didn't. Okay, now we're getting into some seriously futuristic stuff. With EMFI, an attacker doesn't even have to physically touch the device. They can use a tiny, focused electromagnetic pulse, like a surgical EMP, to flip bits inside the chip from a distance and make it spill its secrets. And then, we have the absolute pinnacle of precision, laser fault injection. It's exactly what it sounds like. Using a high-power laser, an attacker can aim at and flip the state of a single transistor out of billions on a chip. This is surgical-level stuff, used in the highest-stakes attacks to pull out a device's deepest secrets. So we've seen the how, but what about the so what? What can an attacker actually do with these glitches? And honestly, the answers are pretty terrifying. I mean, just look at this. This isn't some academic exercise. This stuff is happening out there, right now. We're talking about bypassing the fundamental startup security of a device, stealing the encryption keys right out of your phone, cloning SIM cards, or even taking over the computer that controls your car. It's serious. And that's the absolute heart of the problem, right there. Your fancy antivirus software? Can't stop this. Your firewall? Totally useless here. These attacks just waltz right past all the software defenses because they're not playing that game. They're operating at the level of electrons. Which, of course, brings us to the really tough question. If software can't fix this, then what can? And this leads us to the idea of the unpatchable vulnerability.
I mean, this is the big one, right? The whole security world is built on finding bugs in code and patching them. But what do you do when the flaw isn't in the code at all? What happens when the vulnerability is literally physics itself?
And the honest, kind of scary answer is you really can't. You can't just push out a software update to change the laws of physics, right? You can't patch away electron noise or heat drift. These are physical realities. The only way to defend against this is to design the hardware from the very beginning to be more resilient, which is an incredibly difficult and expensive thing to do. So, here's the big takeaway from all of this. As our entire world gets packed with more and more chips in our cars, our homes, our cities, we have to fundamentally rethink what we mean by security. The real edge, the real wall protecting our data, isn't your firewall anymore. It's the predictable, reliable behavior of electrons. And when that becomes unpredictable, well, that changes everything.